everyone, in today's video, we're going to be discussing logarithms. Logarithms are a really important concept on the AMCs. They typically show up in 1 to 2 problems on the AMC 12 and also sometimes on the AIME. So for those of you who don't know, we're going to start by defining logarithms. A logarithm is the power to which a number must be raised in order to get some other number. Logarithms are expressed as log base b of n, where b is the base and n is the number. Basically, we are trying to calculate how many times we need to multiply the base to get the number. In other words, it's what power of the base do we need to get the number. So let's look at a quick example. When we're trying to find log base 2 of 16, we want to find how many times do we need to multiply 2 to get 16. So in this case, we have 2 times 2 times 2 times 2 equals 16. So log base 2 of 16 is equal to 4 because we needed 4 2's to get 16. Now we're going to talk about logarithms and their relation to exponents. So if we have log base x of y is equal to a, that tells us that x to the power of a equals y. So in our previous example, we saw how log base 2 of 16 was 4. Now applying this relation to exponents, we have 2 to the power of 4 equals 16. Which we know is true. So in most logarithms problems, you're going to want to frequently go between logarithms and their exponents, so this is something that you should definitely be comfortable with. Now let's look at some more examples. For the first one, what is log base 4 of 64? So we want to know how many 4's do we need to multiply to 64, or what power of 4 do we need to get 64. In this case, 4 times 4 times 4, or 4 cubed is equal to 64. So log base 4 of 64 will be equal to 3, and that's our answer. Now let's look at another problem. What is log base 3 of 81? Similarly, we want to find how many 3's need to multiply to get 81, and our answer will be 4, because 3 times 3 times 3 times 3, or 3 to the 4, is equal to 81. So log base 3 of 81 equals 4. Now when we want to find log base 5 of 1, this is a little bit more challenging. We want something where 5 to the power of x equals 1. So for those of you who don't know, all positive integers to the power of 0 equals 1. So in this case, x will just be 0. And that means that log base 5 of 1 is equal to 0. Now let's move on. Now I'm going to look at some examples with log with decimal numbers and fractions. So these are some more complicated applications. So the first problem, we're trying to find what is log base 4 of 128. So basically, what power of x do we need to get to 128? So in this case, you may want to just try multiplying 4's, and you'll see that there's no integer x that satisfies this equation. And that's because x is actually a decimal. So what we want to do in this case is separate 4 into its prime factorization, which is 2 squared. So what we're actually trying to find is 2 squared to the power of x is equal to 128. By exponent rules, we have 2 to the power of 2x equals 128. And because 128 is 2 to the 7, we know that 2x must be equal to 7. And that tells us that x is equal to 7 over 2, or 3.5. So we need 3.5 powers of 4 to get 128. So that tells us that log base 4 of 128 is 3.5. Now let's look at another example. What is log base 2 of 0.25? So this might seem a little bit complicated. So whenever you have a decimal, you want to try and convert it to a fraction. In this case, what we want to do is just say, find log base 2 of 1/4. This makes the problem a lot easier, because now all we have to do is find what power of 2 needs to get 1/4. And this is where we get into negative exponents. In this case, 2 to the power of negative 2 equals 1/4. So x is equal to negative 2, and we have log 2 of 0.25 is equal to negative 2. In our final example, we want to find what is log base 3 of 1 over 27. We do the same thing as in the previous question, where we have 3 to the x is equal to 1 over 27, and we find that x must be equal to negative 3. And that tells us that log base 3 of 1 over 27 is negative 3. Now, this is going to be important for future problems. Log of any negative number, so for example, if we had log of negative 12, this is all undefined. So you can never have a negative number when you're taking a logarithm. Now let's move on. So a special logarithm is base 10. So sometimes logarithms are written without a base, such as when you just have log of 1000. And this just means that the base that we're dealing with is base 10. So an example is if you were told to find log of 1000, all you have to do is find log base 10 of 1000. And this is the same as our previous questions where we're trying to find some x, so 10 to the power of x equals 1000. In this case, our answer will be 3. Now we're going to move on. Another special logarithm is the natural log, which is base e. For those of you who don't know, e is Euler's number, and it's an irrational number which can be approximated to 2.71828. And these are just the first few digits. So a logarithm with a base of e is called a natural log and is written as ln. You may have seen that button on your calculator. So anytime you see ln, all they're talking about is log base e. So an example here is find ln of 7.3891, and we're just trying to find to what power of e can we get 7.3891. In this case, our answer is just 2. Now we're going to talk about some more formulas. These are all extremely important, and I recommend you memorize them so that you can use them when they show up on the AMCs. The first one is the log of base a of a to the r is equal to r. Our next one tells us that log base a of bc is equal to log base a of b plus log base a of c. This is similar but is for division, and that tells us that log base a of b over c is equal to log base a over b minus log base a of c. This is for exponents, and it tells you that log base a of b to the power of c is equal to c of log base a b. So basically you just pull this exponent and move it to the front. Our next formula tells us that log base a of b times log base b of c is equal to log base a of c. In this formula, we see that log base b of a is equal to 1 over log base a of b. And our final formula tells us that log base b of a is equal to log base d of a over log base d of b. This formula is the most important. It's called change of base, and it's how you convert from one base to another. This is going to be useful in many of our problems, so if you don't know any of these formulas, I highly recommend you write them down and make sure you memorize them. Here are some more advanced formulas. These can be useful, and it's nice to know they exist, but you don't need to memorize them for context. Now we're going to get into our first practice problem, and it's from the 2015 AMC 12A, and it says, what is the value of a for which 1 over log base 2 of a plus 1 over log base 3 of a plus 1 over log base 4 of a equals 1? What we want to do in this case is use the change of base formula, and that tells us that log base 2 of a is equal to log of a over log of 2. And in this case, we're just going to work in base 10 and not write any base down, just to save some time and avoid any confusion. So similarly, this tells us that log base 3 of a is equal to log of a over log of 3, and so on. So from here, we're going to convert our expression to 1 over log base a over log of 2 plus 1 over log of a over log of 3 plus 1 over log of a over log of 4. And this is equal to 1. So now we can flip all our fractions, and we get that log of 2 plus log of 3 plus log of 4 over log of a is equal to 1. Because all of these have the same denominator, we can combine them, and by our multiplication logarithm rule, we know that log of 2 plus log of 3 is equal to log of 2 times 3. And that plus log of 4 is equal to log of 2 times 3 times 4. So we can simplify our numerator to log of 2 times 3 times 4 over log of a. And that's equal to 1. Now we multiply by log a on both sides, and we get that log of 24 is equal to log of a. And from here, it's clear that a is equal to 24. And that is our answer. So in this case, what we did is we applied the change of base formula, and then we simplified our logarithms based on fractions and the addition rule. And we got that a equals 24. Now let's move on to our next problem. This is from the 2018 AMC 12B, and it says, what is the value of log base 3 of 7 times log base 5 of 9 times log base 7 of 11, all the way to log base 23 of 27? So this is another problem where the change of base formula is going to come in very handy. We're going to express each of these logarithms as by change of base. So log base 3 of 7 is going to become log of 7 over log of 3. Log of 5 of 9 is equal to log of 9 over log of 5, and so on. So when we replace all of these in our original function, we're going to get an expression of log of 7 over log of 3 times log of 9 over log of 5 times log of 11 over log of 7, so on. And then we have log of 25 over log of 21 times log of 27 over log of 23. So what you can notice is that this sequence is actually a telescoping sequence, and all of our terms are going to cancel out, except for the first two in our denominator and the last two in our numerator. And that just leaves us with an expression that's equivalent to log of 25 times log of 27 over log of 3 times log of 5. So now we're going to use the reverse change of base formula. So log of 25 over log of 5 is actually just equal to log base 5 of 25. Similarly, log of 27 over log of 3 is just equal to log base 3 of 27. So our answer is just log base 5 of 25, which is 2, times log base 3 of 27, which is 3, which is equal to 6. So in this problem, we just used change of base, saw that our sequence is telescoping, and most of the terms canceled out, and then just simplified to get 6. Now we're going to move on to the next problem, and this is from the 2015 AMC 12B, and it says, what is the value of 625 to the log base 5 of 2015 to the power of 1/4? So this problem has a lot going on, so we're just going to simplify it by letting log base 5 of 2015 be x. In other words, we have 5 to the power of x equals 2015. So now we can replace log base 5 of 2015 with x in our expression, and we'll get that 625 to the power of x to the power of 1/4, and that's what we want to find. So this is equal to 625 to the power of x over 4 by exponent rules, and we know that 625 is 5 to the power of 4, so when we replace it, we get that this expression is equal to 5 to the 4 to the power of x over 4. And again, with exponent rules, this just simplifies to 5 to the power of x. And as we previously calculated, 5 to the power of x is just 2015. So our answer is 2015. So again, in this problem, all we did was a simple substitution, and then we simplified. Now we're going to move on. Our next problem is from last year's AMC 12A, and it says there is a unique positive integer n such that log base 2 of log base 16 of n is equal to log base 4 of log base 4 of n. And we're trying to find the sum of the digits of n. So in this problem, we're going to start off by making the expression a little bit more simple by letting both of these terms equal x. So first we have log base 2 of log base 16 of n is equal to x. We can take the power of 2 on both sides, and we'll get that log of 16 of n is equal to 2 to the x. Then we take the power of 16 on both sides, and we'll get that n is equal to 16 to the power of 2 to the power of x. Now we perform similar operations for our right-hand side, and we'll see that log base 4 of log base 4 of n is equal to x. That tells us that log base 4 of n is equal to 4 to the power of x by taking exponent of 4 on both sides, and then we take the power of 4 on both sides again, and we get n is equal to 4 to the power of 4 to the power of x. So for these to be equal, we know that we must have 16 to the power of 2 to the power of x equals 4 to the 4 to the x. So now all we have to do is see that 16 squared is 256, 4 to the power of 4 is also 256, so x being 1 will satisfy our equations. Now all we want to do is find n and the sum of its digits. So we can plug it into either of these equations, and we'll see that n is equal to 16 to the power of 2 to the power of 1, which is 16 squared, which is 256. And the sum of its digits are 2 plus 5 plus 6, which is 13. To recap quickly, what we did in this problem is set our initial equation to x, and then simplify from x on both sides, and then set them equal and calculate x later on. So this is a pretty common trick that you're going to use, and it just helps to keep everything simple and clean to make sure that you don't make any silly mistakes. Let's move on to the next problem. So in this next problem, we're going to use an interesting fact, and it's when you take a logarithm of numbers which form a geometric progression, the logarithms of those numbers is an arithmetic progression. So now let's get into our problem, and this is from the 2013 AMC 12A. It tells us that the sequence log base 12 of 162, log base 12 of x, log base 12 of y, log base 12 of z, and log base 12 of 1250 is an arithmetic progression, and we're trying to find x. So let's say the difference between these terms is d. If their difference is d, that tells us that x is just 162 times 12 to the power of d. Similarly, it means that y is equal to x times 12 to the power of d, and so on. And this tells us that the sequence 162, x, y, z, 1250 is actually just a geometric sequence with a ratio of 12 to the power of d. And that makes our problem a lot simpler, so we're going to work with that instead. So let our first term be a, our second term be ar, let y be ar squared, z be ar cubed, and 1250 be ar to the fourth. So when you prime factorize 162 and 1250, you'll see that 162 is equal to 2 times 3 to the 4, and 1250 is equal to 2 times 5 to the 4. So we have ar to the fourth over a is equal to 2 times 5 to the fourth over 2 times 3 to the fourth. Now we can cancel a from both our terms on the left-hand side, and we can cancel 2 on the right hand. And we'll see that r to the 4 is equal to 5 over 3 to the 4. And that tells us that r is equal to 5/3. Now what we want to do is find x. So we know that x is equal to 162 times our ratio. So 162 times 5/3, which is 270. And that's our answer. So for this problem, we just converted our arithmetic sequence to a geometric sequence, and then we found our common ratio and used it to solve for x. Now let's move on to the next problem. This is from the 2014 AMC 12B, and it says, for how many positive integers x is log base 10 of x minus 40 plus log base 10 of 60 minus x less than 2? So before we begin, we just want to notice that x has to be between 40 and 60. If x was less than 40 or x was greater than 60, one of these terms would be negative, and as we previously mentioned, that's not allowed. They also can't be 0, so our only possible values for x are between 40 and 60. This immediately rules out option choices E and D, because we know that there's less than 20 answers. So even if you can't actually solve a problem, just getting this far in the problem will allow you to get pretty good odds of guessing this one right. So these are tricks that you can use during the actual AMC 12 if you're not able to solve the problem. Now let's work on actually solving it. So first we can use our multiplication rule to see that we can simplify log base 10 of x minus 40 plus log base 10 of 60 minus x and combine them to get log base 10 of x minus 40 times 60 minus x. And we know that that's less than 2. Now we can take the power of 10 on both sides and get that x minus 40 times 16 minus x is less than 100. We can now expand and simplify a little bit, and we get negative x squared plus 100x minus 2400 is less than 100. Now rearranging terms, we'll see that x squared minus 100x plus 2500 is greater than 0. And from here you can notice that this is just x minus 50 squared. and this must be greater than 0. So we know that all squares are greater than or equal to 0, and the only way that this problem will not be satisfied is if x equals 50, which will make our left-hand side 0 and make our expression false. So this problem will work for all numbers between 40 and 60 other than 50. So that's 41 to 49 and 51 to 59. And this is a total of 18 solutions. And that tells us that our answer is B. Great, so in this problem, all we did was use our multiplication rule, expand, simplify, and then find valid solutions, and we got our answer to be 18. Now we're going to move on. So these problems are a little bit more tricky. This problem is from the 2019 AMC 12A, and it says that positive real numbers a and b have the property that the square root of log of a plus the square root of log of b plus log of the square root of a plus log of the square root of b is equal to 100. And all four terms on the left are positive integers, where log denotes the base 10 logarithm. What is AB? So for our terms to be positive integers, we want to find some expression that can represent them. So let's say that the square root of log a is equal to m. That tells us that log a is equal to m squared. And again, we know that log a just means log base 10 of a, so we have a is equal to 10m squared. Similarly, we can do log of b, and the square root of that is equal to n. That tells us that log of b is equal to n squared, and b is equal to 10 to the n squared. So now we want to find what log of the square root of a is, and we can see that it'll just be log of 10m squared over 2, which is just m squared over 2. Now we do the same thing for log of square root of b, and we'll see that it's just log of 10 to the n squared over 2, which is n squared over 2. So we know that the sum of these four terms, m plus m squared over 2 plus n squared over 2, is equal to 100. Now we can multiply both sides by 2 and add 2 to both sides to get m squared plus 2m plus 1 plus n squared plus 2n plus 1 is equal to 202. Now, this may seem familiar because all we did was just complete the square, and we have m plus 1 squared plus n plus 1 squared is equal to 202. So because we know that 2 times 10 squared is pretty close to 200, we can do some trial and error with numbers around 10, and we'll see that 202 is equal to 11 squared plus 9 squared. So now we just solve for m and n, and we'll see that m is equal to 10 and n is equal to 8, or vice versa. In this case, it doesn't really matter because the problem is just asking us to find AB, so it doesn't matter which one is m and which one is n. So now we plug in m equals 10 and n equals 8 back into our original expressions. So here we get that b is equal to 10 to the power of 8 squared, which is 64. And here we get that a is equal to 10 to the power of 10 squared, which is 100. And now when we want to find AB, all we have to do is see that it's 10 to the power of 100 times 10 to the power of 64, which is 10 to the power of 164. And that's our answer. So in this problem, all we did is work backwards to find a valid expression for a and b, and then complete the square and simplify our expression to solve for m and n, and then we plugged them back in and got our answer to be 10 to the power of 164. Let's move on to the next problem. This is from last year's AMC 12B, and it's asking what is the value of the square root of log base 2 of 6 plus log base 3 of 6. So this is another problem where we're going to use the change of base formula. So what we want to see is that 6 is 2 times 3, which tells us that log of 6 is equal to, of some base d is equal to log base d of 2 plus log base d of 3. And we can apply this formula to our expressions log base 2 of 6 and log base 3 of 6. What we'll see is that log base 2 of 6 is equal to log base 2 of 2 plus log base 2 of 3. And our other expression, log base 3 of 6, will be equal to log base 3 of 2 plus log base 3 of 3. So now we can see that log base 2 of 2 is 1 because 2 to the power of 1 equals 2, and log base 3 of 3 is also 1 because 3 to the power of 1 is 3. So this can be simplified to 2 plus log base 2 of 3 plus log base 3 of 2. So now, going back to our formula sheet, if you remember that log base 2 of 3 is actually just equal to log base 1 over log base 3 of 2. So if we express log base 2 of 3 as x, log base 3 of 2 can be expressed as 1 over x. So we can plug those into our equation and we'll see this. So now you can do algebraic manipulation to see that this is equal to the square root of 1 plus 1 over the square root of x. And as you can see here, when you square this, you'll just get our expression that we started off with. So now that we have square root of x plus 1 over square root of x, we can just plug in what x is, and we'll get this is equal to the square root of log of 2, 3 plus 1 over the square root of log base 2 of 3. And again, using our formula, we know that 1 over the square root of log base 2 of 3 is just log base 3 of 2. So we plug that in. And we'll see that this matches option choice D exactly. So our answer is just D. So just to recap, in this problem we saw that 6 is equal to 2 times 3, so we could express log base D of 6 as log base D of 2 plus log base D of 3. We plugged it into our expression, simplified, and used our formulas to get that our answer was log base 2 of 3 plus square root of log base 3 of 2. In this problem, we want to find the value of x that satisfies log base 2 of x of 3 to the 2020 is equal to log base 2 to the x plus 3 of 3 to the 2020. So this is a pretty complex expression, and we want to find some way to simplify it. In this case, we're going to use a change of base formula. And that formula is very handy, and I recommend using it if you can't think of anything else to try. So in this case, we want to find log base 2 of x of 3 to the 20. And using change of base formula, we get that this is equal to log base 2 of 3 to the 20 over log base 2 of 2 to the x. Similarly, we can do this for our other expression over here, and we get that log base 2 to the x plus 3 of 3 to the 2020 is equal to log base 2 of 3 to the 2020 over log base 2 of 2 to the x plus 3. And now we can set these expressions equal to each other. And for our denominator, we know that log base 2 of 2 to the x is just x. Similarly, on our right-hand side, we know that log base 2 of 2 to the x plus 3 is just x plus 3. So we simplify that again. Using our exponent rule, we know that we can pull these exponents out in front of the logarithm. So we get that this expression is equal to log base 20 times log base 2 of 3 over x, and that's equal to 2020 log base 2 of 3 over x plus 3. Now we can just cancel log base 2 of 3 from both sides, and we can cross multiply. That gives us that 20 times x plus 3 is equal to 2020 times x. Further simplifying this tells us that 60 is equal to 2000x, or x is equal to 60 over 2000, which can be simplified to 3 over 100. And again, this problem is looking for m plus n, and that tells us that our answer is just 103. So just to do a quick recap, we started off by using change of base formula to get this expression and this expression. Then we set them equal, used our exponent rule to move these exponents and simplify them. In this step, we canceled terms from both sides of our equation, then we simplified and solved for x, and we got that our answer was 3 over 100, and that meant that what the question was asking for, our answer is 103. This final problem is from the 2019 AMC 12A. It says that positive real numbers satisfy log base 2 of x is equal to log base y of 16, and xy is equal to 64. And we want to find log base 2 of xy squared. So this is another problem where we're going to set our expression equal to some term a, just to make it a little bit simple. So we have log base 2 of x is equal to a. That tells us that 2 to the a equals x. We can do something similar for our right-hand side, where we have log base y of 16 is equal to a. That tells us y to the a equals 16. So because xy equals 64, we want to use that fact somehow. And because 64 is 2 to the power of 6, we want to try and convert x and y to powers of 2. So we already have x equals 2 to the a, and we also know that y to the a is equal to 16, which is 2 to the 4. So if we take the ath root of both sides, we get y is equal to 2 to the 4 over a. Now we can go ahead and plug this in to xy equals 64, and we'll get that 2 to the a times 2 to the 4 over a equals 64, which is, again, 2 to the 6. Here we know that a plus 4 over a is equal to 6. We can multiply both sides by a and simplify to get a squared minus 6a plus 4 equals 0. Applying the quadratic formula here tells us that a is equal to 3 plus or minus root 5. We want to find log base 2 of x over y. And x over y is just 2 to the a over 2 to the 4 over a, which is 2 to the a minus 4 over a. So we want to find what 2 to the a minus 4 over a is. We can start off by trying to find a minus 4 over a. We already know that a plus 4 over a equals 6, so we can calculate a minus 4 over a by saying that we have negative of a plus 4 over a plus 2a. This is equal to negative 6 plus 6, and then plus or minus 2 root 5. So this is just plus or minus 2 root 5. Our final step of this calculation is to plug it back into our log. So we have log base 2 of 2 to the plus or minus 2 root 5, which is just plus or minus 2 root 5. And because we are squaring this expression, the plus or minus doesn't matter, and we get that our answer is 2 root 5 squared, which is 20. And that corresponds to answer choice B. So in this problem, what we did is we first did the pretty constant trick of setting it equal to some variable to make the expression simpler. We expressed both x and y in terms of powers of 2 so that we could plug it into our equation that tells us that y equals 64. We wrote an equation for a and solved using quadratic formula to get a equals 3 plus or minus root 5. We took our desired expression and calculated that we wanted a minus 4a, found it based on our previous values, and got that it was plus or minus 2 root 5, and then we squared it and plugged it into our final expression to get our answer of 20. So that's all we have for today. Thanks for watching. We hope you learned something new, and if you found it useful, please make sure to like the video and subscribe. Bye everyone!